Electricity is one of the most important forms of energy used in modern society, powering everything from homes and hospitals to industries, transportation systems, and data centers. Behind every light switch and electrical appliance is a complex power system designed to generate, transmit, and distribute electricity safely and efficiently. Although several methods of delivering electrical power have been developed throughout history, the three-phase alternating current AC power system has become the worldwide standard because of its reliability, efficiency, and ability to supply both small residential loads and large industrial equipment. Understanding how three-phase power is generated and why it became the preferred choice is fundamental for anyone working in electrical engineering or power system operation. Electrical energy begins its journey at a generating station where mechanical energy is converted into electrical energy using the principle of electromagnetic induction. A turbine driven by steam, natural gas, water, wind, or nuclear energy rotates the rotor of a synchronous generator. As the magnetic field rotates past stationary windings inside the stator, an alternating voltage is induced. If the generator contains only one stator winding, it produces a single-phase AC voltage that rises and falls in a smooth sinusoidal pattern. The voltage changes polarity continuously, completing either 50 or 60 cycles every second depending on the country's electrical standard. This alternating waveform is described by the simple relationship versus T equals V sin omega T, where the voltage changes continuously with time. Although single-phase electricity is suitable for homes and small electrical devices, its instantaneous power fluctuates during each cycle, making it less suitable for large motors and industrial applications. The history of electrical power includes both alternating current AC and direct current DC systems. Direct current flows continuously in one direction and is naturally produced by batteries, fuel cells, and solar panels. DC is ideal for electronic equipment and energy storage applications because it provides a constant voltage without changing polarity. However, transmitting DC over long distances was historically difficult because changing voltage levels efficiently was not practical before the development of modern power electronics. Alternating current, on the other hand, changes direction continuously, allowing transformers to easily increase voltage for transmission and reduce it again for safe distribution. Higher transmission voltage means lower current for the same power transfer, significantly reducing energy losses in transmission lines. For this reason, AC became the dominant technology for national power grids. Today, high-voltage direct current (HVDC) is widely used for specific long-distance transmission projects and submarine cables, while conventional AC systems remain the backbone of almost every electrical network. The true strength of AC systems became evident with the development of three-phase generation. Instead of using one stator winding, engineers place three identical windings inside the generator, each physically separated by 120 electrical degrees. As the rotor turns, each winding generates the same sinusoidal voltage but reaches its maximum value at a different instant. These three voltages are known as Phase A, Phase B, and Phase C. Because they are equally spaced in time, the combined electrical output is remarkably smooth and balanced. Rather than delivering pulsating power like a single-phase system, a three-phase generator supplies nearly constant power throughout the electrical cycle. This smooth power delivery reduces vibration, improves efficiency, and makes three-phase systems ideal for industrial applications where continuous operation is essential. One of the greatest engineering advantages of the three-phase system is the creation of a rotating magnetic field. Each stator winding produces its own magnetic field, and because the currents are separated by 120 degrees, these three magnetic fields combine into one magnetic field that rotates continuously around the stator. Although there are three separate electrical phases, the motor experiences only one smoothly rotating magnetic field. This rotating field naturally pulls the rotor around without interruption, producing nearly constant torque. The speed of this rotating field depends only on system frequency and the number of magnetic poles in the machine. This simple but powerful concept forms the basis of nearly every induction motor used in industry today. The rotating magnetic field also explains why three-phase motors are naturally self-starting. A single-phase motor produces an alternating magnetic field that simply oscillates back and forth, creating no preferred direction of rotation. Consequently, single-phase motors require additional starting windings or capacitors to begin rotating. In contrast, a three-phase motor immediately develops a rotating magnetic field as soon as power is applied, producing starting torque without additional components. This results in simpler construction, higher efficiency, lower maintenance requirements, smoother operation, and longer service life. For these reasons, almost every large industrial motor, pump, compressor, conveyor, fan, and manufacturing machine operates using three-phase power. An important characteristic of three-phase systems is electrical balance. Under ideal operating conditions, the three-phase voltages have equal magnitudes and remain exactly 120 electrical degrees apart. Similarly, the currents drawn from each phase are equal. When this balanced condition exists, many engineering calculations become much simpler because each phase behaves identically. More importantly, the vector sum of the three-phase currents becomes zero, meaning that no current flows through the neutral conductor. Balanced operation reduces equipment heating, minimizes voltage fluctuations, improves system efficiency, and allows generators and transformers to operate under their intended design conditions. Maintaining balanced loading is therefore an important objective for both distribution engineers and system operators. The neutral conductor plays a critical role in practical power systems. Most distribution transformers are connected in a star-Y configuration, where one end of each phase winding joins together to form the neutral point. This neutral provides a stable voltage reference and allows both three-phase and single-phase loads to be supplied from the same transformer. Large industrial customers generally receive all three phases, while residential consumers are typically connected between one phase and the neutral conductor. In many countries this provides approximately 230 volts to homes while maintaining about 400 volts between any two phases. The presence of the neutral also accommodates unequal loading among customers. If one phase supplies more current than the others, the neutral carries only the imbalance current, allowing the system to continue operating safely despite different customer demands. Without a neutral conductor, supplying millions of independent single-phase loads would be significantly more difficult. Electrical power generated at power stations cannot be delivered directly to consumers because transmission over long distances at low voltage would result in excessive current and large energy losses. Instead, generators typically produce electricity at voltages between 11 kV and 25 kV. Step-up transformers immediately increase the voltage to transmission levels that may range from 132 kV to more than 500 kV depending on the power network. Near population centers, substations progressively reduce the voltage through several transformation stages until local distribution transformers provide approximately 400 volts for three-phase customers and 230 volts for single-phase consumers. This ability to efficiently transform voltage is one of the primary reasons alternating current became the foundation of modern electrical networks. Understanding electrical power requires distinguishing between active power, reactive power, and apparent power. Active power, measured in kilowatts kW, performs useful work such as driving motors, producing heat, or illuminating lamps. Reactive power, measured in kilovolt amperes reactive kVr, does not perform useful mechanical work but is essential for establishing the magnetic fields required by motors and transformers. Apparent power, measured in kilovolt amperes kVA, represents the total power supplied by the electrical source. These quantities are related by the simple expression S squared equals P squared plus Q squared. The relationship between active and apparent power is known as the power factor, defined as power factor equals PS. A high power factor indicates efficient utilization of electrical power, while a low power factor causes higher current, increased transmission losses, larger voltage drops, and reduced system capacity. Consequently, utilities and industrial facilities continuously monitor power factor and install capacitor banks or other reactive compensation equipment to improve system performance. Many people are surprised that a household multimeter measures approximately 230 volts even though the actual AC waveform reaches a peak value of about 325 volts. This difference occurs because electrical instruments normally display the root mean square (RMS) voltage rather than the peak voltage. RMS represents the equivalent DC voltage that would produce the same heating effect in a resistor and therefore provides the most useful measure for power system calculations. For a sinusoidal waveform, the relationship between peak and RMS voltage is Vrms equals V peak, square root 2, resulting in approximately 230 volts RMS from a 325 volt peak waveform. This explains why household electrical equipment is rated according to RMS voltage rather than instantaneous peak values. Power system operation extends far beyond simply generating electricity. Modern control centers continuously monitor thousands of measurements every second using supervisory control and data acquisition (SCADA), energy management systems (EMS), phasor measurement units (PMUs), and wide area monitoring systems (WAMS). System operators observe frequency, transmission line loading, transformer loading, bus voltages, active and reactive power flows, voltage stability margins, oscillation damping, reserve generation, equipment status, and contingency security. Every second they ensure that electricity generation precisely matches consumer demand while maintaining secure operation following equipment failures or unexpected changes in renewable energy production. Their decisions are essential for preventing overloads, maintaining voltage stability, and avoiding widespread blackouts. Although many people never see three-phase electricity directly, it is present in almost every aspect of daily life. Power stations generate electricity using three-phase generators, transmission networks transport it over hundreds of kilometers, substations distribute it throughout cities, and industries rely on it to operate manufacturing equipment efficiently. Hospitals depend on three-phase systems to power life support equipment, airports use it for lighting and baggage handling systems, water treatment plants operate large pumps with three-phase motors, and data centers rely on balanced electrical supplies for continuous operation. Elevators, escalators, refrigeration systems, electric vehicle fast chargers, air conditioning plants, railway traction systems, oil refineries, and large commercial buildings all depend upon the stability and efficiency of the three-phase AC system. The three-phase AC power system is one of the most successful engineering developments in history. Its ability to generate smooth power, create a naturally rotating magnetic field, provide self-starting motors, simplify balanced system analysis, and efficiently transmit electricity over long distances has made it the universal standard for electrical power systems. Combined with transformers, the neutral conductor, proper power factor management, and continuous monitoring by skilled system operators, three-phase AC technology delivers the reliable electrical energy that supports modern economies and everyday life. Every time electricity is generated, transmitted, or consumed, the principles of the three-phase power system are working silently in the background to ensure safe, stable, and efficient operation.